All right. Good afternoon, guys. Um, I was thinking about this video yesterday when I heard Jernaism talk about the way flipping from geocentric to heliocentric changed the direction and the speed of the moon, and how it seemed like a very strange thing for him to comprehend. So I thought about it, and it's one of the things I've obviously thought about a few times, and I've tried to lay it out here so that it can make sense. So, in both instances here, we've got an Earth, and it's looking out towards the sun. I've tried to put the sun out in that forward direction there, and I've tried to do a loop where a moon might be. Now, for both these cases, for the geocentric Earth, which is stationary, and for the heliocentric Earth, which is supposed to be spinning, and of course I've drawn it from the North Pole, right, anti-clockwise from north view, right. With both these geocentric and heliocentric, we're assuming that they are both globes. One can be a globe that is just fixed in space, just floating in space, but it's dead fixed. The other one that is spinning, right? Because as far as I'm concerned, the flat pancake model of the flat Earth is not necessarily geocentric, because geocentric means Earth-centered. So that means Earth must be an item or a product or something like that, an object, and everything is centered around that, rather than having just planets and wandering stars floating above you. So anyway, onto the crux of the story, right? So this is day side. If you were on this side, you'd be seeing a sunset. If you were on this side, you'd be seeing a sunrise, right? Now with the geocentric perspective, like the way we look at it every single day, when we look up in the sky and we spot the moon, if you were to look up into the sky at the same time each day, let's say it's either lunchtime, or let's say it's midnight, or let's say it's 10 p.m. or something like that, right? Every single day, if we look up at the exact same time, we would notice that it seems to be roughly 51 minutes behind where it was the day before. And in the geocentric model, the moon, just like the sun, is going east to west. So it's always going from left to right, from a North American, European perspective. It's going left to right. And every single day at that same time, it seems to be a little bit further behind every single day. So when you wake up and you go around and look at the next day, and you look up into the sky, you will notice it hasn't quite made it to where it was the night before, right? And so both the moon and the sun are both going left to right in this particular instance. Now, when you go over to the heliocentric position, right, same sort of scenario with the Earth. Sunset here, sunrise there, night and day, so on and so forth, right? But the Earth is rotating in this particular direction. And so that is going anti-clockwise or counterclockwise, as per what the Americans say, right? But this 51-minute delay that we saw over here, the 51-minute delay over here, is now a day moved, right? And so it takes the moon 28 days to move around the planet in the heliocentric model. So every single day it moves 1/28th, right, of the entire rotation. So it takes 28 days to reach all of these locations, right? And so that basically means that the moon in the heliocentric model moves right to left. So it's moving this direction, right? Whereas in the geocentric model, it's moving that way, right? And of course, I'm just ignoring the sun's position, because realistically, it's moving, we're moving, everything's moving. So I'm just trying to rationalize it just for the moon only. And so, so geocentric, it moves left to right, but it moves one day, right? And it does 28 days to do this whole thing. Whereas with geocentric people are assuming that the moon is basically going around every 23 hours, right? So I've taken, this 51-minute thing, it's a little bit sketchy sometimes, but essentially if you deduct, roughly 50 to 51 minutes every single day to the meridian, I would say, then it takes roughly 20, the moon has basically moved 23, hours or rotational position by the time it reaches 24, if that makes sense. So it seems as if it hasn't made it to the same point each and every day. So in general, the moon seems to have done everything roughly within a day, but this takes 28 days to go around. And so that goes left and this one goes right. So that explains why one goes left, one goes right. This one takes 28, that one takes like 23. Does that make sense? So that is the rotation direction and the time difference. And just to finish it out, of course, moon cycle, roughly 28 to 29 days, depending on, how you judge it, because everything's from like what phase it actually is or where it is from a solar perspective. So if you actually, do 51 minute times 28 days, you get roughly 1,428 minutes. When you compute what 1,428 minutes actually is, it's roughly 1 day. So 1 day in minutes is 1,440 minutes, right? So that's what 24 hours is supposed to be. So essentially you got the 51 minute lag, times it by the 28, which is the amount of moon days for a moon cycle, and you get roughly a day. So that means that completes this, this on the geocentric, on the heliocentric one. It does this in a combination of 51 times 28, right? And so that totals of 1 day, right? So there you go. That's the reason why it goes different direction and different speeds. There you go, Jernaism.